looking a little wild. Good morning, guys. Let's do all that. So this week we have a few things to cover. It's actually a fairly dense week. We want to cover the mean value theorem, we want to cover curve sketching, and we want to cover L'Hopital's rule. So last week we did a little intro to the curve sketching portion of this week's material. Today I want to talk a little bit more about that and a little bit about the mean value theorem. Your book presents these things in a slightly different order than I intend to present them. So we're going to look first at the mean value theorem, then we're going to look at some curve sketching stuff, then we're going to look at L'Hopital's rule, and then we're going to come back to a little bit more curve sketching. So I'll show you here what I mean. The book breaks this up. So you've got MVT, mean value theorem, and then this 4.3 section is really a curve sketching section, and then the section on L'Hopital's rule, and then they come back to talk more about curve sketching. So that's what we're doing this week. We're covering these three sections. Let's see. I'm going to turn the screen share back off for a second while I get the .cam fired up. Oh, that's right, I can't remember what I'm doing. Okay. There we go. And folks pile in. Set the resolution. Oh, that's the. Let's get the slide out of the way. That's good. Okay, so you guys back here. There it is. Okay. A few other little announcement-y things. I did finish over the weekend going through and grading all of your rewrites for exam 1. And once I finished that, I updated the exam 1 scores and then duplicated them in the second assignment to get you to the total of 100 points for exam 1. So the gradebook for exam 1 is up to date and finalized. And I posted an announcement on Canvas talking about that. So exam 1 scores have been adjusted for the rewrites and finalized. My goal is to get the gradebook totally up to date this week. To do that, I need to enter your study guide scores. And there's still a lot of folks who haven't handed in study guide 1. So if you haven't done that, please, even though it's late, please go ahead and do it, right? I'm not the sort of person to penalize people for late work. And I would much rather see your work on the study guide than not see it. It'll allow me to give you some more useful feedback. And as we get ready to start preparing for exam 2, which you will start preparing for at the end of this week, you really want all that feedback you can have from the exam 1 material. So if you haven't handed in study guide 1, please do so. Okay, I don't care that it's late. The purpose of the study guides is not to ever hurt you. They're only ever supposed to help you. And I would hate to see people's grade go down due to the study guide. That's not something that I ever really have happen in my in-person classes, and I don't want to have it happen here. But on the other hand, I do have to stick to the syllabus, so I can't just omit those grades for those who didn't turn them in. But what I can do is I can be very understanding about handing it in late. So that's what I'm trying to do. So if you didn't turn that in, please turn it in. So today we're going to talk about mean value theorem and how derivative affects the shape of the graph. So these are sections, I think, 4.2 and 4.3 respectively. Yeah, mean value theorem is section 4.2, and how the derivative affects the shape of the graph is 4.3. So we're going to start here at MVT. So before I present to you the full mean value theorem, there's kind of a little version of it, and that'll help you understand why the full version is true. And there's a kind of a cute story I like that goes along with this. So imagine I was driving from here to Orlando, right? It's say 100 miles, and there's a cop in Gainesville, and he gets on the radio when he sees me leave, and there's a cop in Orlando, and he gets on the radio when he sees me arrive. So they can communicate to each other how long it took for me to get there. And if the cop in Orlando, when I arrive in Orlando, knows that I set out 1 hour ago, he can pull me over and give me a speeding ticket right away. Why? Even if I'm not speeding at that moment, he can pull me over and give me a speeding ticket. Because if I traveled 100 miles in 1 hour, then you can be certain that at some point I was going at least 100 miles an hour. Maybe I went 100 miles an hour the whole time. Maybe I went 40 miles an hour and then 200 miles an hour and then 60 miles an hour. But the only way for me to cover that distance in that amount of time is for me to have gone an average of 100 miles an hour over the whole distance, which means at some time I had to be going exactly 100 miles an hour. That's really the statement of the mean value theorem. Mean means average, remember. So this is the basic idea. So the sort of gentler theorem that we use to build up to the mean value theorem is called Rolle's theorem. And it says this: if f of x is continuous on the closed interval AB and differentiable on the open interval AB, and f of A equals f of B, then for some C in the open interval AB, is it open or closed? I always forget this last part. And for some C, and yeah, in the open interval AB, f primed of C is equal to 0. Okay, so this is Rolle's theorem. Rolle's theorem says if you're continuous on the closed interval AB and differentiable on the open interval AB, so you just think of smooth function restricted to a closed interval, and the y values at the endpoints match, then somewhere in between, for some C in the open interval AB, you had a horizontal tangent line. I'll show you the picture that goes along with this. Here's A, here's B, and let's say f of A is equal to f of B. They're both equal to this y value. In between, I can do anything I want, as long as it's smooth and continuous, right? So maybe I come down like this and come up like this and something like that. What Rolle's theorem says is that there has to be at least one horizontal tangent line Now, as I drew it here, there are two. So you could take this to be a value C, maybe call it C1, take this to be another value C, call it C2. What Rolle's theorem says is that if the y values at the endpoints match, then the only way to connect them with a smooth curve is if you have at least one point where the curve turns around. Maybe you're totally flat, right? Maybe the graph of f is just the horizontal line. And in that case, for every c in AB, f prime of c would be equal to 0. But no matter how you connect them, the only way to connect them smoothly is is in such a way that you end up with a hill like that or a valley like that. And then the mean value theorem, the theorem that this section talks about, is a generalization of this theorem that says, okay, well, what if these 2 points aren't on the same horizontal line? What if the endpoints aren't there? Well, then I can imagine drawing the line that connects those 2 points, and somewhere there has to be a parallel tangent line. That's the idea. So before I move on to MVT, questions about Rolle's theorem. The statement of the theorem, why it's true.
Professor.
Yes.
Is that all you did from the beginning of the class? Because I didn't see the link until now. Like it wasn't showing on the canvas.
Yeah, so this is all we've done so far.
Okay. Okay, thanks.
So I talked a little bit, I said the exam 1 rewrites have been graded. If you didn't turn in study guide 1, please do it, even though it's late. Today we're going to talk about mean value theorem, that's this section, and how derivatives affect the shape of the graph, which is section 4.3. So really the only thing we've done so far is talk about Rolle's theorem. And what Rolle's theorem says is, if you have a smooth function and you look on the interval AB, you look on some closed bounded interval, if your smooth function has the same y value at the endpoints, then somewhere in between you have at least one horizontal tangent. And as I drew this here, it has this horizontal tangent, and maybe even one more right here. Yeah. So the only way to connect 2 points at the same height with a smooth curve, or any way you connect 2 points at the same height with a smooth curve, you must have at least one horizontal tangent line in between. No matter how you try to avoid it. If you try to avoid doing that, you'll either end up making the function non-differentiable, like you'll end up making one of these things pointy, or non-continuous. So if your function is continuous and differentiable, i.e. connected and smooth, then you're guaranteed to end up with at least one horizontal tangent in between. I think geometrically it's very reasonable and intuitive, but the proof is not super reasonable or intuitive. I don't know if your book goes through a proof. They do. And in each case, it relies on some facts about the derivative. So using Fermat's theorem, yeah, that works. Usually I use something else when I prove this, but no, that's cheeky. Yeah, I'm not a fan of that proof. So this is kind of the baby mean value theorem. This is the intro to mean value theorem. And the way you go from this to the mean value theorem is by allowing the 2 points at the end to be at different heights. Any other questions on this guy? So a classic kind of problem, although it's not super fun, would be for me to give you a function and a closed bounded interval and ask you to find the numbers C guaranteed to exist by Rolle's theorem. To do that, you would take the derivative and set it equal to 0 because Rolle's theorem guarantees the existence of horizontal tangent lines. So it's the same sort of shit that you've been doing. But MVT is a little bit more interesting. The hypotheses of the mean value theorem are the same. Says says if f of x is continuous on the closed bounded interval AB and differentiable on the open interval AB, then there exists a number C in the open interval AB such that f primed of C is equal to the average rate of change, which is f of B minus f of A over B minus A. And the picture that goes with this is very similar to the Rolle's theorem picture, except now I don't require that A and B have y values at the same height. So here's the idea. If you take the slope of the line connecting these 2 points somewhere in between there must be a parallel tangent line. So to me, that appears to be about here. So this would be C. So this is a tangent parallel to this secant. And what mean value theorem says, if you have a nice smooth continuous curve on a closed bounded interval, then at least one point in the interior of that interval, there is a tangent line parallel to the secant line. So you have to remember what a secant line is. A secant line is a point connecting, or a line connecting any 2 points on a graph. So here, 2 points on the graph, the line that connects them is a secant line. This guy right here is the slope of the secant. And of course, f primed of C is the slope of the tangent. So what the mean value theorem is really saying is that you give me a secant line, I can find you a parallel tangent line in between the 2 points that make up the secant line. Think of this as the cops measuring my average speed from Gainesville to Orlando, and this is the point where I earn the ticket. Even if they don't observe me at this point, they can guarantee that there's a time when I'm traveling at that speed because they know my average speed. So if you know the average rate of change, you can be guaranteed the existence of a point where the instantaneous rate of change, the derivative is a rate of change, it's an instantaneous rate of change, is equal to that average rate of change. And again, here, as I've drawn it, there's more than one such point. It looks like there would be another one right here. So I'm going to call this C1, maybe this is C2, where you have another tangent line, which is parallel to that secant line. And no matter how you try to connect those dots with a smooth, continuous curve, this will happen. There's no way to connect the 2 dots here and here with a nice, smooth, continuous curve without there being at least one point where the tangent line is parallel to the secant line. So I'll give you a minute to get all this down in your notes, and then we're going to solve 1 or 2 little problems, but then we're going to move on, because MVT, well, it's beautiful. And it's really useful for proving things about functions in higher math classes, like analysis classes or advanced calculus classes. It's not super duper useful from our perspective. There are some fun things we can do with it, like proving the existence of solutions to certain equations, but it's not useful for like straight solving problems, at least not the sort of problems that we usually solve. Any questions on the statement of the theorem? Can anybody see how if I relaxed this condition, if I didn't require f to be differentiable, we could escape the conclusion? Like, why is it necessary that the function be differentiable everywhere in the open interval AB? Is there a way to connect these two dots with a curve that is not smooth, which would allow you to avoid this? Imagine I had a curve that just went like this and then like this. So y is differentiability required if we remove the hypothesis that f is differentiable everywhere in AB. Is the theorem still true? Let me see if I can draw a curve that's not smooth everywhere and avoids doing that. So I'll draw the picture very similarly here. If I did something like this, this guy is not differentiable. Right, he is differentiable everywhere over here and everywhere over here, but he's not differentiable here. Here's the secant line. Notice that nowhere in here is there a parallel tangent line. What do you think? So if you relax the differentiability condition even a little bit to allow there to be one point where the function isn't differentiable, the theorem is no longer true. We need the function to be smooth everywhere in order for this theorem to be true. So most people think of the mean value theorem as a way to understand what exactly it means for a function to be differentiable on an interval. It's a fairly tight restriction, right? Saying that a function is differentiable everywhere on the open interval AB is a big assumption about the function. And if you allow my function to not be differentiable even at just one point, then the theorem is no longer true. Because there isn't a smooth transition from this piece to this piece, I never get a part of my curve where the tangent is parallel to this secant line. So the idea of transitioning smoothly from one slope to another slope, that requires that you take all the slopes in between, right? Like here, if you look up here on the graph of the first function I drew, here the slope is positive, and over here the slope is negative. And since this function is smooth, that means every slope in between this positive number and this negative number is attained. If you imagine the tangent line over here, it's like this. If you imagine the tangent line over here, it's like this. And every single slope in between that positive and that negative number has to be attained somewhere because of the nice, gentle, smooth transition. Without that nice, gentle, smooth transition, you don't get every possible slope in between. And in particular, you won't get the slope of the secant. So being differentiable everywhere in the interval AB is what makes this go. And the reason we like to talk about this theorem in Calc 1, even though it's not super duper useful for problem solving, is because it helps you wrap your head around exactly what it means to be differentiable everywhere on an interval. And what it really means, the way I encourage you to think about it, is that you have these nice smooth transitions, and smooth transitions on F mean that F primed is continuous. And in particular, F prime satisfies the intermediate value theorem. That's the real big deal here, is that if you have a continuous function, then its derivative, if you have a differentiable function, then its derivative automatically satisfies the intermediate value theorem. You might want to say that its derivative is continuous. That's actually not true. But to find a counterexample to that claim is quite hard. And the way we call this in an analysis class is we say that the derivative of a differentiable function is a Darboux function. Darboux is a French mathematician after whom the theorem is named. And it just says that a function is Darboux if it satisfies the intermediate value theorem. So if f of b is greater than f of a, then every value in between is attained. So here, if the derivative goes from being positive to negative, then definitely somewhere in between it has to be 0, and somewhere in between it has to take every value between the value of the derivative here and the value of the derivative here. And that includes the slope of this secant line. So if you're not super into the theory, it's understandable if this is a little bit intractable. I encourage you to read this section of the textbook. It's a good section. And we'll solve 1 or 2 little problems here. You can see the pictures that they've drawn, very similar to the pictures that I've drawn. And they do go through a proof. Right. The proof, first you prove Rolle's theorem, and then you use Rolle's theorem to prove MVT. The proofs are not super exciting for us. But let's see if we can find, here, we need to do a slightly more primitive example first. I'm going to grab one out of the exercises. Let's see, verify, satisfies the hypotheses, find, Let's look at this guy. So I'm going to write this down, and then I'm going to come back to the doc cam. We're going to verify that f of x equals x cubed minus 3x plus 2 satisfies MVT on the interval -2 to 2, and find the number C guaranteed by MVT. Okay. So what does it mean to satisfy MVT? It means that you're continuous on the closed bounded interval and differentiable on the open interval. So f of x is continuous on the closed interval -2 to 2 because it's a polynomial. And polynomials are continuous everywhere. right? That was actually a theorem that we proved way back in section 2.5. F of x is differentiable on the open interval -2 to 2 for the same reason, because it's a polynomial. And polynomials are differentiable everywhere. Okay, so my function is continuous on the closed interval. It is differentiable on the open interval. Therefore, by MVT, there exists, or there is some number C in the open interval -2 to 2, such that f primed of C is equal to the average rate of change for f of x on the interval -2 to 2, which is f of 2 minus f of -2 over 2 minus -2. And to find that number C, I need to calculate this, calculate f primed, and set them equal to each other, and then solve. So this guy, we will calculate f of 2 is 2 cubed minus 3 times, should that be a square? Nope, 3 times 2 plus 2, which is 8 minus 6 plus 2. Eight minus 6 is positive 2, plus 2 is positive 4. And f of -2 is -2 cubed minus 3 times -2 plus 2. That's -8. Minus 3 times -2 is plus 6 plus 2. -8 plus 6, that's -2, plus 2 is 0. So f of 2 minus f of -2 over 2 minus -2, that average rate of change is 4 minus 0 over 2 minus -2 is also 4, so this is 1. So the number C I'm looking for is a solution to the equation f primed equals 1. Primed. Oh, I'm sorry, I can't quite hear what you're saying there, Angelica. Could you say that a little louder?
Yeah, so at the very top it says, find the number C. Is that guaranteed by MVT?
Yes.
Cool, thanks.
Yep. Yeah, so remember MVT says if f of x satisfies certain hypotheses, then there's guaranteed to be some number C such that some other shit is true. So what we're doing here is we're looking for the number C guaranteed to exist by MVT. So MVT promises me that there is some number C such that the tangent line at that number is parallel to the secant line. So what we have here, this guy, this is the slope of the secant line. And so f primed gives me the slope of the tangent line. So what I'm going to do is calculate f primed and set it equal to that. And then the solution to that equation will be this number C, where the tangent line is parallel to the secant line. So f primed of x, if we look back at f, we differentiate just using the power rule. It's an easy derivative. This piece becomes 3x squared minus 3 because the x differentiates to 1. So what I need to do, hence, we want to solve, solve 3x squared minus 3 equals 1. And this is not a super hard equation to solve. You could do it one of two ways. You could pull the 1 over here and then factor. But since there are no regular x terms, there's just x squareds, I could also add that 3 over. And I get 3x squared equals 4. And then I can divide by the other 3, and I get x squared equals 4/3. And then take square roots. So x would be plus and minus. The square root of 4/3 is 2 over the square root of 3. Now remember, the square root of 3 is about 1.5. So this is like 2 divided by 1.5. So both of those are actually in the open interval -2 to 2. So we have two values of c. C1 is -2 over square root 3. And C2 is +2 over the square root of 3. And that's the game. Now, most problems having to do with MVT, most simple problems having to do with MVT are just like this, right? I give you a function and an interval, and I ask you to find for me the number C that's guaranteed to exist by MVT. It's not the only thing we can do. There are some more interesting problems, and I want to do one more, slightly more interesting problem. But this is your standard thing. So first I'll give you a second for anybody who's still writing. But then I want to look at the graph in Desmos. While you're writing, if I had gotten 2 solutions out of this and one of them was bigger than 2, I would throw that one away because that would not be a part of this open interval. Here, both of these solutions happen to be in this interval. If you check with a calculator, you'll find that both of these are between -2 and 2.
Why is it that we don't use the power rule to solve?
We did. So I used the power rule to calculate f primed here. The x cubed differentiated to 3x squared, and the 3x differentiated to 3, the +2 differentiated to 0. So I use the power rule when I calculate the derivative. This does kind of look like the sort of thing that you would use to find a derivative, but notice that I'm not taking any limits. I'm just plugging in numbers here. So rather than getting a tangent line out of this piece, what I'm getting is a secant line because I'm not taking any limits. And what we're saying is that the tangent line, which we can talk about his slope coming from the power rule, somewhere has to be parallel to this secant line.
Oh, okay, because f of 2 is x cubed minus 3x plus 2.
Yep.
Okay.
So another way of thinking about this is that if I had here a limit, and maybe this was an x and this was an x, and I was sending x to -2, then I would be getting out exactly f primed of -2. But rather than doing that, we're saying this thing, which is an average rate of change without the limit, not a derivative, has to somewhere be equal to the instantaneous rate of change, which is the derivative. So the object that you take the limit of to get the derivative is equal to the derivative somewhere. In other words, this is not a horrible approximation for this, if you want to think in terms of approximations, especially if this interval is very, very small. As you shrink this interval smaller and smaller, this thing gets closer and closer to this thing. And what we're saying is that even without the limit, somewhere they are equal. So I'm going to switch over to Desmos now and look at that graph really quick and see if we can't make these connections. So I'm going to look at the graph of f of x. Oh, minus 3x plus 2. And I'm going to restrict to the interval -2 is less than or equal to x is less than or equal to 2. So there's that guy. My secant line is the line connecting these points. So let me see if I can't draw that in somehow. Let's say, what's that slope gotta be? 2. And when intercept there is 2, so this would be y equals 2x plus 2. No, x plus 2? Yeah, like that, okay. And I'll draw this in with a dotted red line. And again, I'll restrict to -2, less than or equal to x, less than or equal to 2. So this red dotted line is the secant line for that function on that interval. And what mean value theorem says is that somewhere in there, there is a parallel tangent line. And what we found is that there looks like there's 2 points like that. One of them is 2 over the square root of 3. So we'd have this point comma f of that value. I'll just copy paste it. And then the other guy is at the positive 2 over root 3. So if you look at the slope of the tangent line right here, that tangent line will be parallel to this secant line. Let me add in that tangent line. I'll need the derivative, 3x minus 3. I don't want to graph him, but I do want y minus g of this number. Sorry, y minus f of this number equals g of this number times x minus this number. Wait, what did I do here? I fucked something up. Oh, this is ugly. So I don't want to spend too much time in Desmos. Can you imagine the tangent line here? Can you see how that tangent line would be parallel to this? We'll do the calculation for one of them. So it should be y minus f of a equals f primed of a. Oh, this is 3x squared. That's where I fucked up. Okay. So y minus f of equals g of times x minus. Yeah, there we go. All right. So I'll do these in blue. See how the blue line is parallel to the red dotted line? Because at this point, the derivative has the same value as this secant line. And I can do the same thing at the other guy, y minus this guy equals g of this guy times x minus this guy. Right, over here, again, the tangent line is parallel to the red secant line. Okay, so there's no need to really restrict this. So the blue are parallel, blue dotted lines are parallel to the red dotted lines. So these 2 points are the points guaranteed to exist by the mean value theorem. C1 and C2. All the mean value theorem does is it says, if you know the secant line's slope, then you can be sure that somewhere in between those 2 points, between these 2 endpoints, there is another point where the tangent line is parallel to that secant line. And that's what we have illustrated here. The blue lines are the tangent lines, which are parallel to the red secant lines. Okay, so that's MVT. MVT just says, you give me a secant line, I guarantee you there is a tangent line parallel to it. I'll leave this for just a minute more, and then we're going to look at some other problems we can solve with the mean value theorem. One of the fun things you can do, because what the mean value theorem does is it relates the values of the original function to the values of the derivative. I think your book has one or two fun examples like this. Yeah. Okay, suppose f of 1 is 10 and f prime is greater than 2. How small can f of 4 be? So number 25 here is fun. I'm going to copy this down and then we'll take a look at that. If f of 1 is 10 and f primed of x is always bigger than or equal to 2, then for 1 less than or equal to x less than or equal to 4, how small can f of 4 possibly be? Okay, so that's the setup. And what I like about this problem and problems like this is that it feels like you don't have enough information. It feels like they've told you very little. They told you the value of the function at 1 point. They told you that the derivative is always bigger than 2. And then they ask, how small can this possibly be? So kind of what they're saying is, here you've got a point on the graph. 1, 10 is on the graph of f. And here they tell you that the rate of change for the function is always bigger than or equal to 2. And they want you to use that information to figure out the smallest f of 4 could possibly be. So it's like, if you start here and you never go faster than this, how small could that be? I guess it's really, if you start here and you never go slower than this, how small could this be? So let's write down what MVT says. MVT says there exists a number C in the open interval 1 to 4 such that f primed of C is equal to f of 4 minus f of 1 over 4 minus 1. Some of this stuff I know, some of this stuff I don't. F primed of C, I'm not going to do anything with him yet. F of 4, that's what I'm trying to figure out. F of 1, I was told that's 10, so this is f of 4 minus 10 all over 3. 4 minus 1 is 3. They asked me, how small could f of 4 be? What's the smallest possible value for f of 4? So somewhere I'm going to need an inequality. And they've told me here that f primed is always bigger than or equal to 2. So this thing is guaranteed bigger than or equal to 2. Right? So I know that 2, f primed of x is always bigger than or equal to 2. So in particular, f primed of C is bigger than or equal to 2. So this object right here is at least 2. And that is equal to this. So this has to be at least 2. Therefore, 2 is less than or equal to f of 4 minus 10 over 3. right? Saying f prime of c is greater than or equal to 2 is the same as saying 2 is less than or equal to f prime of c. Let's get that out of the way first. That's how inequalities work. You can just, if Joe is taller than Sally, is the same as saying Sally is shorter than Joe. That's what's going on here. Now, if Joe is equal to this shit, and Joe is always taller than Sally, then Sally is shorter than this shit. So take a second to think about the inequality work that's gone on here. F primed is always bigger than 2. So this particular value of f primed of c, is guaranteed bigger than 2 because f primed of x is always bigger than 2. This is a particular value of the derivative, and we're told that the derivative is always bigger than 2, so this particular value needs to be bigger than 2. Another way of saying that this is bigger than 2 is that 2 is smaller than this, right? If Joe is taller than Sally, then Sally is shorter than Joe. It's the same statement, just rewritten. Now I take this information and I plug it in here. If f primed of c is equal to f of 4 minus 10 over 3, and f primed of c is bigger than 2, then this thing has to be bigger than 2, because that thing is equal to f primed of c. Now I can take this inequality and solve it for f of 4. So if I multiply both sides by 3, I get 6 is less than or equal to f of 4 minus 10. And then I add 10 to both sides and I get 16 is less than or equal to f of 4. So f of 4 can be no smaller than 16. This is sort of my favorite style of MVT problem, because it's kind of surprising that you can make this claim about f of 4 given just the information you had. But really what they're telling you is that you're starting at 1, your value is 10, and your rate of change is always at least 2. So for every 1 you go over, you have to go up at least 2. Maybe you go up more, but for every 1 you go over, you've got to go up at least 2. Between this x value, 1, and the x value that we're asking about, 4, that means you had to go up 2 for every 1 you went over. Well, you're going over 3, right? Between 1 and 4. And since you have to go up 2 for every 1 you go over, if you go over 3 times, you have to go up at least 6. So if you're starting at 1 comma 10, then you march all the way over to x equals 4, you have to have gone up at least 6. That means you have to be at least at 16. I'm going to keep this here, and I'm going to draw a little picture for you guys. Okay. We're going to say this is 1 comma 10. And here's a line with slope 2. So over here would be 4 comma 16. And what they're saying is that your curve can do whatever the hell it wants, but it always has to be increasing at least the same rate that this line is increasing. So maybe it wiggle wobbles up here, something like this. But once you get to this point, you have to be above this point. In other words, f of 4, which is this y value, has to live above 16. Because your function is increasing at least as fast as that dotted line. That's what it means to say f primed of x is always bigger than 2. It means that your function is increasing at least as fast as that line. Neat shit, right? So I'll bring this back again for anybody who needs more time to write something down. These are your sort of two classic MVT problems. Either find the value of C guaranteed to exist by MVT, or use MVT to get an upper or lower bound on some function value based on some bound on the derivative. So if your function's always growing at least the rate of change 2, and you're starting at the point 1 comma 10, then when you get out to x equals 4, you have to be at least at 16, because for every 1 you go over, you have to go up at least 2. And the slowest way you can do that is by staying along the dotted line that I drew a second ago. But the mechanics of the problem involve a little bit of work with inequalities. And I know that that's work that not everybody is super great with. Takes practice, and it's not trained as much as it should be. In pre-calc, if you took pre-calc with me, we did a lot of inequality work, but I know that's not always the case. So this is really all I intend to say about mean value theorem. Are there any questions about this particular example or mean value theorem in general that you guys would like to look at? Okay, if not, then I am going to introduce section 4.3. Section 4.3 is in a way the opposite of section 4.2. 4.2 is all theory, very little skill building. 4.3 is all skill building. So section 4.3 is super important, and that's where the majority of your homework this week is going to come from. This is how the derivative affects the shape of the graph. Okay, and there's a few big results in there. The first one we've already mentioned. I'm going to check to see exactly how your book phrases it, because I want to give you precisely what they do. Yeah, okay. So if f primed of x is greater than 0 on the interval AB, I should say on the interval so you don't confuse it with a point, then f of x is increasing on the interval AB. And also, if f primed of x is negative on the interval AB, then f of x is decreasing on the interval AB. This is something we've talked about, but we've never said formally, so here it is. If you have a differentiable function and its derivative is positive, then the function is increasing. If the derivative is negative, then the function is decreasing. The picture that goes with this is fairly straightforward. A positive tangent line means you got to be increasing, a a positive sloped tangent line means you got to be increasing, and a negative sloped tangent line means you got to be decreasing. So for example, if I look from here to here, everywhere between A and B, no matter where you look, the tangent line has negative slope. So here, everywhere. On the interval A to B, the tangent line has negative slope. And that's the same as saying f primed of x is negative on the interval AB. And you notice that everywhere the tangent line is negatively sloped, the function is decreasing. F of x is decreasing on the interval AB. All right, so just a little example here. But if you look at the tangent line here, the slope is negative. Here, the slope is a little bit more negative. Here, the slope is starting to come back towards positive, but it's still negative. Right at these endpoints, the slope is 0. But everywhere in between, the slope of the tangent line is negative, and also the function is decreasing. And that's not a coincidence. That's what this theorem is saying. It says if f primed is negative, i.e., if the slope of the tangent line is negative, then the original function is decreasing. And you can imagine how this would go if I flipped the picture over. If f was increasing, then the tangent lines would all have positive slope. And it goes both ways. So one of the main problems we need to solve in this class is I give you a function, you tell me where it's increasing and decreasing. That's some shit that you did back in pre-calculus. Even way back in college algebra, we do that. But in those settings, I always give you the graph. Here, you don't have the graph. Right? I mean, for this picture, I drew a graph. But the idea is that this theorem will let you find where a function is increasing and decreasing, even if you don't know what the graph looks like. So I'll solve one little problem like that, and then we'll have to stop for the day. So I'll grab this out of your book. There's no harm in that. Extreme. So we're going to talk about the first derivative test on Wednesday. We'll talk about concavity on Wednesday. Inflection points are cool. Where do I have a nice example? Let's look at, where's a nice cool exponential function that's not all fucked up? Find, yeah, okay. Let's look at this guy. X to the 4 e to the negative x. So find
Assuming so, can I take the picture for the last page?
Sure.
Okay, thank you.
Welcome. Find any intervals on which f of x equals x to the 4 e to the negative x is increasing or decreasing. So this is the problem. Remember that increasing means f primed of x is positive. decreasing means f primed of x is negative. So if I want to find where a function is increasing or decreasing, I need to find where its derivative is positive and negative. So I need to calculate f primed. This is a product rule thing. That's x to the 4 times e to the negative x, all primed. So that will be, first I differentiate the x to the 4, and I leave e to the negative x alone. And then I add that to what I get by leaving x to the 4 alone and differentiating e to the negative x, right? Remember, that's the product rule. The derivative of x to the 4 is 4x cubed. So this first piece is 4x cubed e to the negative x plus x to the 4 times the derivative of e to the negative x. That's a chain rule thing. Remember, e to some stuff is always going to differentiate to e to that stuff times the derivative of that stuff. So by the chain rule, the derivative of e to the negative x is e to the negative x times -1. So altogether here I have 4x cubed e to the negative x minus x to the 4 e to the negative x. So this -1 makes that plus a minus. I will factor out the e to the negative x. And what's left is 4x cubed minus x to the 4. And I want to know, where is this positive? Where is this negative? Because this is f primed. And if f primed is positive, then f is increasing. If f primed is negative, then f is decreasing. Does anybody remember how to solve the inequality? This shit is greater than 0. It's definitely something we do in pre-calc. The game is to factor. So we need to solve the two inequalities. F primed of x is greater than 0. That will tell me where we're increasing. And f primed of x is less than 0. That will tell me where I'm decreasing. And I can solve both of them at once by factoring and drawing a number line. So I'm going to go a couple steps further here. This is e to the negative x times, I can factor out an x cubed. And what will be left is 4 minus x. So this is e to the negative x times x cubed times 4 minus x. Each of these factors gives me a root for f primed. Gives me a place where f primed is equal to 0. So if I plot all of those on a number line, this guy is never 0. This guy is equal to 0 at x equals 0, and this guy is equal to 0 at x equals 4. Those, in other words, are my critical numbers, 0 and 4. I plot them on a number line, and then I test a point from each region. If I plug in x equals 1, so test x equals 1, that's from this region, f primed of 1 is e to the negative 1, which is positive, times 1 cubed, which is positive, times 4 minus 1, which is positive. This is e to the negative 1 times 3, which is greater than 0. So f primed is positive everywhere in here. Since both of these are odd multiplicity factors, we will change sign as we jump over each of their critical numbers, which means f is decreasing here, and that interval is -∞ to 0. This region tells me f of x is increasing on the interval 0 to 4, and this region tells me f of x is decreasing on the interval 4 to positive infinity. So that's it. That's how you find where a function is increasing and decreasing. You take its derivative, you set the derivative equal to 0, or you find the critical numbers, you plot those critical numbers on a number line, and then you figure out whether f primed is positive or negative in each of those regions. And you can do that with test points. Here I tested just one point, and then I used the multiplicity trick. But you could also test a point from each region. So I could plug in -1 here, 1 here, and 5 here to find that f primed is negative, positive, negative, like that. Or you can use that multiplicity trick. I think it's possible that not everybody remembers the multiplicity trick. And it's possible that some people never even saw it. It depends on how good your Calc 1 class was, or sorry, Calc 1. Depends on how good your pre-calc class was. So I will post something to Canvas to remind you how to solve nonlinear inequalities, because it's very important here. This sort of thing is what you'll be doing for the most part in your homework this week. There will be a few mean value theorem problems like the examples we did. So if you get into the homework and you're having a hard time with some of the MVT stuff, go back and rewatch this video. And then on Wednesday, we will do more of this, considerably more of this stuff. And then as we move out of Wednesday and into Friday, we'll talk a little bit about indeterminate forms and L'Hopital's rule. That's not really connected to this. I want to stay focused on the curve sketching, so we're not going to worry too much about that. In fact, I may banish it until after exam 2. We'll see. This is the big deal right now. Right? So taking derivatives and using derivatives to figure out where a function is increasing and decreasing. It's hugely important. Any questions on this example, how we did this calculation, or where anything on the page here came from? Can I see, just by a show of hands, how many remember this number line test point thing? Right, no derivative stuff, but you can use the react button there to show me. How many remember solving nonlinear inequalities with test points? Okay, so not everybody. That's about what I would expect. That's fine. Remember, take a look at your test scores. Everything is finalized in the gradebook now. Look at the comments that I left. If it just says, you know, great job, I'll update your score, then everything was perfect. But if there are more notes there, then there's more stuff that you want to look at. If you have any questions for me about how I scored the rewrites or what's going on with your exam 1 grades, don't hesitate to ask. You can send me a Canvas message or an email, or you can come by my office hour this afternoon. But that is it for today. So I'm going to go ahead and stop the share. And I will see you guys either in office hours this afternoon or Wednesday in class. Remember to keep an eye on the homework and watch for that new one that's going to be coming out today with lots of mean value theorem and curve sketching stuff. Okay? I hope you guys have a lovely rest of your morning, and I'll see you either this afternoon or Wednesday.